video, just my screen shows up on the recording. And is this, and then with regards, the other thing I want you all to be aware of before we get started with this is if you go onto the Canvas page and click on quizzes, you will see that there is a quiz for each person's presentation. It will ask you really difficult quiz questions that include what did you like about the presentation, what could be improved about the presentation, and a score of 1 to 10 in the 3 categories, and each one of them tells you the rubric. So you can work on this as you go, or right after class, or tonight. Get it to me by midday tomorrow, so I can start working on grades, but it's fine if you take till tomorrow. They won't show up with the deadline. All right, so there's that. Let me make that go away. Okay, so I will start with the answers to the Matthew Sturm mysteries here. So first, this is just another cool picture that Matthew took. He calls it snow filigree. It's a close-up of snow hanging outside his house, just falling off the roof. Here's our schedule. I'll start, and then we're going to hand it off to Michelle, Stephen, and Friedrich, because Michelle and Friedrich have to run to another class. Then you can see the remainder. We'll check back here if we forget what order we're doing. And I will mute my audio, and I think I will run sharing the screen. So my vote was this picture was of a cabbage. It is not really a cabbage. Matthew says it's a strange set of bubble curtains in clear lake ice that they found last April near Innaviat, which is very far north in Canada, near Canada borders with Alaska. And Matthew does not know what caused these bubble curtains. They're definitely cool looking. The snowmobiles, he gave a much longer answer to, which I won't go into all the details. This is posted if you want to read it all. Basically, the yellow one is his old snowmobile and has a special thing to keep his beard from freezing too much. And the red one probably needs that added, but otherwise the red one is way faster and doesn't bump as much, but might have trouble in trees that are close together. And exactly what they do to snow, I think they both compress them, and he's starting with the red one this winter, so he'll report whether it compresses the snow more than the yellow one. All right, so now let's see if I can get Stephen's links to work here. Stephen, you want to help me out and tell me which one you want me to start with?
Yeah, they're in order there, so that first one should take you to a Jupyter notebook.
Okay.
And we're also going to share it in the chat window so everyone else can follow along as well.
Excellent. All right, how does this look? What do you see?
Yeah.
Are you getting feedback? Do you want me to mute myself here?
No, that's okay.
Okay.
So if you can, I mean, maybe you can zoom in a little bit, like Control Plus. I don't know how well others can see it, but we just put the link in the chat box. So if you want, you can also pull it up on your computer and follow along. It should be good. This will probably just help us drive a little bit. I guess you're going to have to drive for us.
How's that?
An interactive
Perfect.
component, so that'll, yeah.
Yeah, this is going to be tricky. So we wanted to highlight an interactive plotting library just to make it easier to zoom into different time slices when you're exploring data. So since we can't interact with those plots and you're going to have to do the interacting for us, this should be interesting.
We'll be like mission control and you are our mission.
All right. Okay, so give you guys an overview. So interactive SUMA modeling or SUMA plotting with Bokeh is our presentation. I'm Friedrich.
I'm Michelle.
I'm Stephen.
Our presentation has 3 components. The first is why Bokeh? What is it? What can it do? Bokeh is a Python plotting library that lets you render interactive plots. You can save them as HTML documents and then quickly share them with your collaborators and kind of zoom into, explore the model outputs without writing new code just to look at a different time slice. So it's a powerful library that we wanted to use to explore 2 case studies. One was the snow water drainage example from homework 1F, and the second one was the albedo example from homework 1E. The snow water drainage one was, we changed capillary retention, hydrologic conductivity, melt water exponent parameters, and saw what that did to SWE. And then for homework 1E, albedo, we were changing the decay rate parameter as well as switching between a variable and constant decay rate scheme. Okay, so let's scroll down a little bit and we can kind of move through this relatively fast. All right, so here we're loading in some libraries. We create a function to just open the netcdf files. We load in the netcdf files that we created with the drainage, snow water drainage example. So you can keep going down. Here we're loading in the files. We concatenate them using pandas into a single data set. And we can keep scrolling. And I'm going to move through this fast because we're going to get to highlighting the library and then exploring the data with the bokeh plots. So here we plotted up. We're looking at 4 years. But as we all recall, it's kind of hard to tell what's going on. So you need to zoom into a particular time slice. So then we rewrite some code and we zoom into 1 year. And again, we're creating a new cell block. We're generating a static plot. We can tell there's something going on in the data as SWE is decreasing, the drainage is increasing. That makes sense, but we really want to zoom in further. So we take a look at the melt season, June to March. Again, we're writing a lot of code here just to look at different time slices. We see there's a lot of exciting stuff going on. We want to look at the start of the melt season, so we write another block of code. And we're looking at the beginning of the melt season. And again, Michelle is going to go into the analysis of what's going on here in just a second. Now we might want to look at the mid of the melt season. So again, another block of code. And now we want to look at the end of the melt season, and again another block of the code. So you see what the problem we're leading up to here is, wouldn't it be nice if we just had one plot where we could zoom in to different time ranges? So we keep going down a little bit here. And this is where we introduce Bokeh, right? So, yep, keep going down. Bokeh lets you render a single interactive plot. And as you can see here, Jessica, on the right, there's a couple different buttons. And the second one from the top, or the third one, I guess, that one. If you click that, you now have a way to zoom in on any time frame that you want, right? So you can just draw a box and it will quickly zoom in to that area, right? And I'm going to share this particular plot, or hold on. I'm going to share these plots in a second so everyone can be doing this. So this is just a single plot. It lets you zoom into different time ranges. That's great. But we want to look at snow water drainage and SWE side by side. So let's move to the next one. You can also create 2 linked plots. And here's where, if you scroll over to the right a bit, I'll make the window larger, you can get that same button back. And now if you zoom into a particular area, it's going to zoom in on the right plot, but also on the left plot. Okay, so you can see what this library can do. And now the final example at the bottom is it will create an HTML file. And so here we're not plotting in the notebook, and we're going to transition in just a second, but we're generating those interactive plots as a single HTML file, which you can then send to your collaborators or just use as a tool to interrogate the data. So I'm going to transition here, and I'm going to, oops.
It's the second link that I sent you.
Yep. So let me hand it off to Michelle.
Thanks, Friedrich. So once we get this interactive plot loaded, we can actually do a little more exploration into the snow bits. So what we're going to see is, again, those two linked plots of snow water equivalent and liquid water drainage side by side, all for years, linked by the x-axis, and you have those options of panning, of zooming, and then moving from time period to time period pretty quickly without having to rewrite any code or without having to scroll excessively. You might want to open it up in Safari.
Open it up in something else? What do you want it in?
Safari is a good browser, yeah. It tends to load slowly in Chrome.
You want it in Safari? Okay, I'm launching Safari just a minute.
And
Maybe John respond.
No.
No. Let me just post that in the chat.
Okay. So Jeffrey, can you not? Jeffrey says he can see us but can't hear us.
Can you hear me? I'm on the phone listening to you now.
I can hear you.
Can you hear me?
Yeah, I can hear you.
Okay, yeah, I'm on the phone listening now, so.
Okay, you should be able to get links to these are in the PowerPoint that's on the Canvas site if you can't see us live.
We also just chatted it to everybody.
What?
Yeah, I can see the live.
Okay. Okay, so now I'm gonna make this as big as I can. Okay.
And that will be the second link titled Plot Snow Water Drainage, HTML. And open that up in Safari.
What is it? You see it? Is this my screen?
Yep. And if you if you're on a Mac, then do the Command plus and increase the size a little bit. If you're not,
I
don't know.
Joys of there, look, it did something. Okay.
That's fine. We'll work with that, and people have a link to explore on their own as well. So that's another topic that we wanted to emphasize. That this is primarily for exploration and collaboration. If you are presenting at AGU, this is probably not something you want to pull up, something interactive that might take forever to load or break on you, or et cetera, if you don't want that kind of excitement in your presentation. But fine for this demonstration. So we, again, have the 4 water years of the model runs, and then all the drainage parameters are located in the legend. The default parameters are highlighted in blue. Capillary retention is in orange. Hydraulic conductivity is in green. And the meltwater exponent, it looks like it's also in green. Imagine it in red. And then all the combined parameter changes are in purple. So with this, if you want to take a little magnifying glass, Jessica, you can zoom into water year 2002 and look again at those melt season time periods. One other component that Friedrich added to this plot was the selection. So if you wanted to find the individual values of snow water equivalent and the date, you could actually hover and highlight them to see what those actual values are. And as it loads, what we will be seeing, and what you can do on your own, is you can flip between each of the water years and see that, well, at the beginning of the melt season, instead of focusing on, okay, all these different parameters, you can just look at the colors and say, what's happening when? Is anything happening on your screen, Jessica?
No, I mean, I seem to be able to load better on the prior one.
It's a little slow.
I mean, I also have like, oh, there it is.
So yeah, if we wanted to zoom in a little more, we would see that the yellow line is peeling away really quickly in about mid to late March. So that's the early melt season. Yep, so that orange yellow line is the first to peel away. Again, the purple line is all of the parameters that were changed combined into one single simulation. And on the left plot, you'll notice that there are also peaks in the liquid water drainage from the snow profile with those same colors. So the purple all combined, and then the yellow, which is reduction in capillary retention. So that's one thing to note, early melt season. And if we wanted to move on to mid-melt season, we would notice that as snow water equivalents started decreasing, you see these corresponding peaks in liquid water drainage. And the changes in the other parameters will start to be seen as the melt season moves on. But if we want to click on the, it's like two arrows pointing at each other in a circle, Jessica, that'll take us back to the original view, and then we can zoom into late melt season, mid-May to late May. You can do that too. You can do whatever you want. That's the selling point of this.
I tried. I zoomed out. Now what was it just?
And if we want to go just past May 2002, that tick mark, and zoom in there.
It's telling you something. Okay. Am I supposed to? No, I'm supposed to not use my wheel anymore. I'm supposed to switch to the other one, or?
I think if you unclick the wheel, it'll be easier, and just click off of the plot.
Trying. It's very, very slow.
Yeah. So that's another bit to understand, is that there are so many data points that we're visualizing right now, and Stephen will go into a little detail about that rendering process and how we can be more efficient with our time. And as we continue to zoom away, if we wanted to look at different water years, we would notice the same sort of pattern. Early on in the melt season, that yellow line peels away first, and then as the melt season moves on, all the other simulations catch up. And at the end of the season, it's really that yellow line that peters away last. So if we think about the equations and the question from homework 1, part 2, what affects liquid water drainage the most in terms of the parameters that we changed, is really that yellow line, which is reducing the capillary retention by a factor of 3, I believe. And that's all well and good, but it's going back to what you start out with, Jessica, is always double checking, does this make sense? Does it make sense? And if you think about it, and if you wanted to go through the math, or if you just wanted to run through things conceptually, it seems to make sense. Capillary retention is basically a threshold that needs to be reached before liquid can actually start draining through the snowpack. Hydraulic conductivity, which is the first green line, is the ease with which fluid actually moves through the snowpack. And then the meltwater exponent parameter is just parameterizing the distribution of pore sizes. So when you're thinking about, okay, spatial distribution of pore size versus ease with which you can move through the snowpack versus a threshold you have to reach before liquid can even start draining, it conceptually makes sense that the capillary retention is the dominant parameter in this situation for liquid water drainage. So that'll wrap up what we have for the liquid water drainage, but I just wanted to say really quickly that all this code was Friedrich did most of the heavy lifting with coding this up. Thank you, Friedrich. But it was also really easy to adopt for Stephen and I. I don't have much coding experience, but I was able to generate some albedo plots pretty quickly. And Stephen will talk a little bit more about that.
Yeah, the second link that we shared in the chat window in the last 90 seconds, we can look at.
So stay in Safari?
Yeah, that'd probably be safer. So one thing about the amount of data in these plots had us thinking about resampling data and what's really important and what kind of questions we're asking. You know, do we really need a data point every second, or can we work with, you know, hourly or even daily data for, you know, depends on what kind of questions we're asking. And so with this one, we actually just subset to 1 year. And this was the experiment with the albedo, where first we started off with a variable decay parameterization of albedo, and then changed the parameterization scheme to a constant decay rate. And then the result of that change is the large difference you can see between the blue line, which is actually hidden behind the purple, but you can zoom in and explore that. The change from the blue line to the red line, where switching from the variable decay rate to the constant decay rate really decreased overall decay and led to an increase in SWE. You can see in that central plot. But then changing the actual parameter value of that constant decay rate results in the purple line, bringing it back down to sort of more close in agreement with the default variable decay rate. And you can explore this plot as will. At will, there's a few things I could point out, like looking at during the melt season where the largest differences are. Temperatures don't always match between the three model schemes in their timing or magnitude, and snow water drainage, the bottom plot there, is actually, you can see, is quite reduced when that snow albedo decay rate is decreased a lot, meaning that we're retaining a lot more snow and snow water in the snowpack. All these plots and the code for all these are available on GitHub, and we've also included a link to a HydroShare resource which has these. And again, these are these HTML files are kind of great for exploring and sharing the data, not so much for presentations, but for getting a first impression and being able to quickly generate plots. And even there's a little save icon on the top right, and if you click that, you can download a figure of whatever you're looking at, whatever you've zoomed into. Saves a graph for you, so you can put that in your presentation. I think that's all we have. So we'll take any questions at that time.
Yeah.
Yes.
Thank you.
Right. In the interest of time, let's go for one question while I work on figuring out what the next presentation is to put up. Hopefully the question doesn't require me zooming in anywhere. No, that's what we've got here. All right, Ava, Benjamin, and Josh, are you ready?
Let's see. Can you hear us?
I can hear you. Let me know if you're getting feedback and want me to mute myself.
No, we're great. All right, so my name is Josh Suderman. I'm here with Ben and Ava, Ben Serpa, Ava Cooper, University of Nevada, Reno. And our final project looked at the effect of the wind profiles on snow water equivalent. Next slide, please. So in looking at this question of how do wind profile parameterizations influence SWE, we went to homework 2, exercise E, which looked at both the force and the clearing and different wind profile shapes and how those interact with long wave to see how SWE is influenced on the output end. Next slide. So it's just a quick review here. We have a convenient Vic model overview figure, but if we focus in on the blue diagrams within this figure, we know, as discussed in class, that wind presents a few challenges when it comes to estimating its effects on turbulent fluxes. And so, oftentimes we're measuring wind right near the snow surface, maybe 2 meters off of that. However, wind above the canopy is much stronger. It is influenced in a pretty complex way by the canopy continuing down from above the canopy to the snow surface. And all this together affects the turbulent fluxes and ultimately the snowpack. And so we focused in on the canopy wind profile. Next slide. And try to answer this question of, what is the best shape of this profile when trying to model SWE? Again, next slide. And so SUMA presents 2 model options that we can explore, a logarithmic and then exponential shape. And so in logarithmic situation, we have less wind near the snow surface and therefore smaller turbulent fluxes, whereas with the exponential option, we have higher winds and therefore higher fluxes. And so we're going to talk about, Ben's going to talk about how this affects our SWE models throughout the year in Oregon.
Next slide, please. So initially, we just plotted the observed data from Stark in 2000 for the entire season, from December to April. And then next slide. So after that, we used 2 long-wave radiation estimations. We used the Bokeh long-wave radiation estimation with a logarithmic wind profile, and similarly, the TVA long-wave radiation with the logarithmic wind profile, and the rescaled wind, which is the observed long-wave radiation on the site, again with a log below canopy profile. And we found that all 3 of them consistently overestimated SWE throughout the season, but did pretty well in the accumulation zone or accumulation time in December. The reason that we chose Bokeh and the TVA is because Bokeh had the lowest long-wave radiation estimations and typically produced the highest SWE in the model results, and the TVA produced the highest long-wave radiation and the lowest SWE. And then to compare this to exponential wind profiles below the canopy, next slide, please. We ran the same simulation with just by changing the wind profile below the canopy to exponential, and we can see that all the models fit pretty well in the December accumulation, but then there's a pretty large divergence in for mid-December or so, and then in late December, around the turn of the year, something clearly happened there. And then it also fits pretty well in other areas, but the main take home is that exponential wind profiles fit accumulation better, but didn't fit up the ablation zone very well. So Ava's actually going to discuss some finer details at 2 points in this plot here.
All right, next slide. So we're going to focus on these 2 higher SWE periods where some models do perform well. So you can hit next slide. So the first plot is December, where we see our logarithmic wind profiles tends to fit the shape of the observed SWE pretty well. And our exponential profile ablates very quickly and does not fit quite as well. So we're assuming that the exponential profile has too high of turbulent fluxes in December. And then in March, we have low turbulent fluxes or lower turbulent fluxes with the log profile. So our long wave, or calculated long wave, matters a little bit more, and we see this divergence in our long wave values. And then with the exponential profile, we're matching accumulation well. We don't see huge differences between our long waves, but we still ablate very quickly. So the bigger take home is if we have to calculate our long wave value, that's going to affect which under canopy model decision we might choose. So if we're using Bokeh, then we see that it's performing pretty well under the exponential profile. But if we choose something like TVA, we might pick the log profile and adjust more to bring that late season SWE back down. So in general, from this qualitative assessment, we find that maybe you just need to turn a few more knobs. So next slide. Albedo could be adjusted, or albedo decay rate could be adjusted to bring down our melt rates, and under the log profile, this would bring SWE closer. Or if we're using the exponential profile, we could adjust our frozen precip multiplier, because it is possible that our precip can has undercatch of snow. And then we can also adjust our canopy decisions, such as canopy shortwave and canopy emissivity, to get the models to fit better. And any questions?
Seven minutes.
One thing, just have a comment, is that each of those profiles, they're 2 different functional forms, but they each also have different parameters. So you can actually also change the parameters within each of the 2 of the logarithmic and the exponential, and really nail in exactly how much wind you want under your canopy. I think the take-home message, if you don't have measurements under your canopy, it's pretty hard to know what the right answer is. All right, so I believe that's this one again. Yep. All right. So Louis, Jeffrey, and Juan Pablo.
Everybody.
Hi, can hear you.
Great. Where are my mates? Got Juan Pablo in the house.
Can you hear me?
I can hear you.
Yep.
All right, great. Okay. So there's one. What about Lewis? Lewis with us?
You're looking at me.
Okay. Yeah.
Cool. Okay, so hi everybody. We're gonna talk about the same thing. So that's good. You've already gotten a refresher on what the wind profiles are talking about. We're also going to be interested in the wind speed itself, and we're more so concerned with how snowpack sublimation is affected by these various parameterizations in the SUMA model, rather than trying to, best model observational data. So hopefully we'll have a couple of different little pieces of analysis in this presentation. Next slide. Come on, Pablo, you want to take over? Or not?
One. You there? Okay. I'll take over for one then. We had one go through, and he found us this article about wind effects on snow cover in Pascua, Lama, and dry Andes of Chile. And next slide, please. So the goal of the paper that we reviewed was they were looking at the application of distributed snow models, and they were trying to see the effects of the wind on snow-covered patterns, especially in elevated areas where you have a lot of the snow blowing and the glaciers forming. And you can see that the study area is kind of marked by the little red dots in that there. But it has an elevation range between 2,600 and 5,630 meters above sea level, and there's very little vegetation above 3,800 meters. And the study area, they had glaciers occurring on the southern slopes, and some of the highest peaks between 4,780 and 5,480 meters above sea level. Next slide, please. So the research that they did. Pardon?
Can you hear me now?
Yep.
Yeah, sorry for that. What is happening with my computer? So, yeah, as Jeffrey told, thank you. So, in this case, this paper, there's no model that this paper used was running using the data from 11 weather stations over a complete snow season. So we need to consider that we are in the southern hemisphere. So the season is opposite here. So we consider data from May to November. So due to the low precipitation, high solar radiation, the glacier cover is small in the dry Andes, and even the low air humidity, high solar radiation, and strong winds result in large sublimation rates. So the authors consider the wind effects on the snow cover due to snow drift, that is suspension and saltation, blowing snow sublimation in order to understand the effect of wind, cover and glacier formation in the dry Andes. So this is one picture of one of the 11 stations in the dry Andes. Can you go ahead to the next slide? Okay, yeah, so in this picture you can see the snow mass balance component average. In the top image the glacier, and in the bottom image the non-glacier area. And if we see, even they were considering the area above the 4,400 meters above the sea level, that is the minimum glacier altitude. And if we see in the top image the pink dashed line that belongs to the wind transport. So the result in this case, the wind transport of snow is positive on the first half. Is positive on the first half of the simulation period, and is negative in the non-glacier areas. As a result, at the end of the period, the net transport values are 6 millimeter water equivalent for glacier, and 26 millimeter water equivalent for non-glacier. So this result show that glacier don't gain or lose much mass by wind transport, while outside glaciers wind erosion is significant. So next slide. Okay, so yeah, in this plot we see the wind speed on the left axis. On the right axis we have the solar radiation, that it is represented with the blue lines. So the glacier areas, in this case, this plot shows that the glacier areas receive much less solar energy than the non-glacier areas, especially during the spring and summer, and that is from September to December. And this can be explained by the shading that the glacier are mostly found on southerly slopes and are thus more shaded from the sun. So because they are in this area, it's opposite like here, the south-facing slopes are more protected from the sun, and they have more snow or ice bodies. And even the preferential deposition of wind transported snow from glacier-free areas onto glacial surfaces during the winter period. So in the next slide, as a conclusion, this model suggests that the blowing snow sublimation strongly affects snow mass balance in the highest areas where glaciers are founded. Even the result of this model with the wind transport has a lower effect on the overall snow mass balance, and this is partially due to the limitation of the model. This is one of the several limitations that the author pointed out, together with the characteristic of the study area, which is a complex terrain leading to complex wind fields, and even the complexity of the physical processes involved in the wind-snow interaction. So that is all.
So for our modeling, after we were considering what they did in that paper, we used the rescale of the wind canopy from homework 2, and everybody's familiar with this graph by now. If we can go to the next slide. So then we took the snow model and we wanted to see the effects of the wind speed, so we reduced the wind speed down to 1/4. And you can see then that the forest, the amount of snow under the forest goes crazy. It jumps way off the chart there. So we can obviously see then that with having less wind, we're going to get more accumulation under the canopy. But then, okay, if we have less wind, what happens if we double the speed of the normal wind? And then we can see the next slide that we've doubled the wind speed, and during January, because of the doubled wind speed, we lose everything underneath our canopy in the forest. we actually had our snow water equivalent drop to 0. So we had too much blowing, and nothing was allowed then to basically accumulate underneath the canopy. And we can still see that in the clearing, even with double the wind speed, we're still getting we're still getting close to the observations. Next slide, please. So then we wanted to kick it up one more notch and take it up to 4 times the wind speed. And at this point, the under canopy barely has a chance to accumulate. It drops out even before January and barely recovers until March when there was a big event. So we can definitely see that the effects of the wind speed at the ground level are definitely affecting what's going to be landing underneath our canopy. Next slide. And then this is the effects of the wind speed on our snow sublimation. And we can see that for the forested times 4, we get the really big drop. So basically, the effects of the wind on our snow sublimation, if we increase anything above normal wind speed, we're going to start seeing a decrease then in the snow accumulation or an increase in the snow sublimation. Next slide for Juan then. I'm sorry, yep, for Lewis.
Yeah, I'll take over. So yeah, that was kind of the answer to how wind speed affects snow sublimation, but we were also interested in the wind profile. And we've already had that explained by the previous group, so we can go ahead to the next slide. That just shows you a little example on that picture. So I wanted to keep wind speed in the canopy equals to 1.6 times wind speed at the ground because that was the, scientific assumption that gives us pretty good results. So what we see here is a difference between the exponential and the logarithmic wind profile, and the exponential severely drops in SWE, and we see that same disappearance of the snow mass in very late December. And clearly that is a concern because the observations do not show that. So we want to understand, why are we losing the snow mass? So go ahead to the next slide, and we can try to understand what's happening here. So we clearly see that the snow depth drops to 0 at about December 29th, I guess we could call that, and the snow surface temperature as a result climbs above 0. So we're definitely seeing total and complete melt of the snowpack. Go ahead to the next slide. And we can explore some of the fluxes that may have led to that. So we're seeing, a little bit of snow sublimation, well, not a little bit, quite a lot on the exponential curve, peaking in the positive at about the same time that we're getting a huge spike in snow drainage in the exponential curve. And again, then we also just have the sensible heat over here on the right that shows a pretty big spike in the exponential curve at about the same time, around December 29th. We're also seeing these big spikes of sensible heat and snow sublimation around the 17th, which I think may have a factor in losing the snow mass. Since we get such steep sublimation and sensible heat loss, we're seeing, a pretty steep decline in SWE there that then kind of gives us the final push over the edge on the 29th that lets all of the snow drain out the bottom. But one strange thing about this is why we're getting positive snow sublimation while we're getting such steep drainage, and that appears to just be a result possibly of frost covering the snow layer, the top snow layer, that then results in kind of an insulated layer that keeps the bottom of the snowpack warm, kind of the same way that ice on a lake keeps the bottom of the lake warm. So maybe that's why we're seeing positive sublimation and such steep drainage. That's my guess. I don't really have a good answer to why this occurs. I just wanted to try to see, what exactly was going on at this point in time. So if we just go to the next slide, we kind of see some general relationships of the effect of wind profile. So you see the surface temperature definitely climbs above 0 because we're losing that snow mass on the exponential. Definitely less snow depth, less snow drainage overall, which is interesting. But I guess that's just because we have much less accumulation, so there's not as much snow to drain. And of course, the wind profile has a severe effect on snow sublimation, as we see in the bottom right corner, with those spikes, those massive spikes compared to the logarithmic curve. So that kind of answers that question of how the wind profile affects snow sublimation. And last slide just goes to show how the snow layer temp is changing. And I thought this might give us some insights into perhaps why we're getting so much drainage. And we're definitely seeing some persistent warm layers as time goes on. But I just wanted to show as kind of a comparison between the two. We're definitely a little bit warmer on the top of the snow layers with the exponential wind profile than the logarithmic, but the logarithmic stays warmer at the bottom for longer. So again, I'm not exactly sure how that relates to our strange loss of snowpack, but that is those are our results. That's it. Any questions?
Thank you. So what you're showing, I just lost it. There you go. You're actually showing a classic rain on snow event with what's going on right here, going down. And so remember we talked about the latent heat of evaporation versus latent heat of sublimation. So you condense what you're showing here with your, or was it your snow sublimation? The really positive snow sublimation right here is water condensing on the surface of the snowpack. And it's actually using the energy content of the snowpack to condense that water, which is then warming the surface of the snowpack all the way up to 0 and melting the snow in the process. And so it's actually, people think that you might want to check if it's raining on that day. You look at the net time series.
Right. That's a good point.
I think it's actually a classic rain on snow event where you have very strong, both sensible heat flux, you have warm air, and it's very humid, right, because it's raining. And so you're actually condensing water on the surface of the snowpack, and it's that process of energy release or energy, the energy associated with condensing water that's melting the snowpack.
Gotcha. Well, I think we can just safely say that the wind profile still has an effect by, allowing less snow to accumulate and therefore causing that rainfall event to have a much more drastic effect than the
different, not the rain. So it's the water vapor. So the wind is actually assisting that transfer. So with low winds, you won't have the transfer. So the vapor transfer is wind dominated. So it's not the rain. So it is the wind.
Okay. Gotcha. Thanks.
Yeah, but no, great plots. Any other questions? Well, I had some.
Hey, can everybody hear CUAHSI 9?
Yes. Can you hear me?
Okay, great.
All right, cool. Just turn on this later. Yeah, if it wasn't. Okay, I'm Cassie.
Justin.
I'm Jordan.
And so this is our final presentation, and we're all at the University of Washington, which is why Justin and I are together right now. Go to the next slide. Okay, great. So Michelle, Friedrich, and Stephen already touched upon the second problem from homework 1, which is kind of where we got our idea from, which is what we're diving into. And so we're going to be looking at the temperature distribution profile and the liquid water drainage in the snowpack. And so that's involving the energy heat flux
and also the water flux between soil and snow. So you'll see that later. What we're looking at is water year 2000. And so we defined like a specific event in the melt season that we're going to be looking at, which you can see there, and then also the early melt season, and then like the mid to end melt season, what we're looking at. But it would be helpful to have Michelle and Friedrich's and Stephen's plotting tools here, because it would be really simple. Okay, next slide. How's it going? Okay, cool.
Sorry, I think we have a lag on our end. But.
Yeah, so, all right. So these are some of the questions that we're looking to answer in this presentation is, you know, what parameters are actually contributing to the overall meltwater amounts and also the timing of that melt. So these parameters that the first group already touched upon is the capillary retention, the hydraulic conductivity, and then that exponential, the exponent parameter. And Zeron's going to show the actual equations in the next slide for those, so you guys can see how they're involved in the single model. So we're also looking at what years are sensitive, and so basically a sensitivity analysis for timing. So Zeron, do you want to talk about this?
Yeah. So the competition here shows the different process, and the rate at water now is a function of the capillary as a fraction of the
Getting some weird feedback. Other names are
Do you hear it now?
Yeah, it's better.
Okay. So indicated by blue, and the snow means essentially hydraulic snow, and about water flow essentially green block. So when we change the parameters, they all lead to faster drainage, but we're gonna look into what's their actual impact and how much and which one leads to the most dramatic impacts. So if you could go to the next slide. So here we plotted the accumulative drainage for water year 2000 and also their differences compared with the default CLM parameters. As we can see, the reduction in FCAP has the most dramatic change compared with the others, and we looked into 3 periods of this snow process: the early of the melt, the middle of the melt, and the end of the melt. If you could go to the next slide. So the timing of the melt is different for all. With the reduction of fractional, with the reduction of FCAP being the most dramatic one, and it has the earliest melt beginning and followed by some other experiments. And during the middle of the melt, as we can see, their patterns are quite similar, although their amount is different. So, so some brief information for the plots. The top row is the drainage rate. That's the melt rate from the snowpack, and the second one is the cumulative drainage, and the third row is the difference between those accumulated drainage. So in the middle panel, the left panel is the start of melt, the middle panel is the middle of melt, and the right panel is the end of melt. So in the middle of the melt, we can see their pattern is very similar, except for that the exponential causes some fluctuations in the differences. Their pattern is the pattern of its melt is different compared with others. And the end of for the end of melt, the reduction of FCAP has the earliest melt off date, but as you can see, their slope seems to be similar to each other. And then in the next slide, we plotted the temperature profile we plotted temperature profile of the soil, both the soil and the snow. As we can see, when there's melt, the soil is actually cooled by some snowpack runoff events. But as you can see from the upper panel and the lower panel, those two panels, the upper panel is the default and the lower panel is the reduction in FCAP. They don't show too much differences. That's why we didn't look too close into the heat flux or the temperature transfer between those two, the soil packs and snow packs. What we look into is more the fraction of liquid water content in the soil, which Justin will take over from here.
Still muted. Can everybody hear me now? All right, sorry. Like Zoran said, it was really difficult to see with temperature necessarily. So instead, we decided to move to a variable that's more indicative of what's going on, the actual transfer between the snowpack and the soil column. And so what we looked at was the fractional liquid water content. So that's essentially a variable between 0 to 1 that tells you what % of that layer of either snow or soil is actually liquid water at whatever time. So both you can see as it goes into the soil column how those columns actually increase in liquid water content going from blue to yellow. You can actually see how the water is percolating in, and then also the speed at which it does if there's any curvature. You see that, in December, as it percolates a little bit slower, there's some sort of curvature there. So this should both imply percolation events and speed. So if you go to the next slide. As Zoran mentioned, we had those 3 events. So we had the early, middle, and late runoff events. So taking a look at this early event to start out with, we're taking a look at the 2 parameterizations that produce the most different percolation, the most different runoff patterns from the snowpack. And what you see, we're showing the default on the top, and then the reduced capillary retention profile on the bottom. The liquid water contents are ranging between 0 and 35%. And you can see for the capillary retention, it's happening much earlier. This is around March 6th, which March 5th, March 6th matches with that map on the lower left. What happens much later for the default parameterization. So if you go to the next slide, Michelle touched on this really well, and just to go into this a little bit deeper, SUMA actually percolates water based on this equation here, where you have some reduction to the saturated hydraulic conductivity based on a relative saturation, and that's the quotient there. And SUMA only percolates water at times where this numerator is positive. So in other words, the fractional content of liquid in the snow is greater than the residual holding capacity of that snow. So what we really think, if you go to the next slide, is happening here is you see that the snowpacks above the soil at this time are not actually that different. They're about within 5% of each other. But when we reduce this capillary retention parameter from 0.6 or 6% to 2% of the pore space, essentially it was able to hold 6% of the pore space full of water. Now it's able to hold 2. That made all the difference, and the liquid water that was present was actually able to move out of the snow and percolate into the soil column. So like I said, Michelle touched on this earlier, but in this way, the capillary retention parameter actually controls both the frequency of runoff events and then also the amount that runs off, because you'll see that relative saturation will change as the residual holding capacity does. So if you go to the next slide, we also wanted to take a look at the middle runoff event. We decided to skip the end of the season runoff event because things look very similar, and it was really kind of hard to pull things apart, and really splitting hairs there. But these are the 4 plots for each of the 4 parameterizations. You have the default in the upper left, the reduced capillary retention parameter on the upper right. Those are the 2 that are significantly different, the most different, you would say. And then on the bottom, you have the reduced meltwater exponent, and then the bottom right, you have the reduced or the increased hydraulic conductivity. And we could sit here all day and take a look at these tiny differences. But if you go to the next slide, I pulled out some of the most dominant things that we saw from these plots and some hypotheses. So the snowpack composition overall at this time in the middle of the melt season seems to be somewhat similar. Like I said, the differences are on the order of less than 5% typically. But what you saw with the capillary retention parameters is that the altered runoff frequency, so because we're reducing the amount of water that the snow can hold, it was more willing to allow runoff. And then you also saw these more isothermal spikes, or sorry, less isothermal, more diurnal swings in the snow liquid water content, as the water that was available at the top through melt was able to make it through the snowpack within a time. And then it cooled overnight and it warmed, and it cooled overnight and it warmed repeatedly. You didn't really see that, for example, in the meltwater. So that's the bottom left one. You saw more of a homogeneous ripened snowpack where there was a lot of water in there, and it percolated at a slower speed. So more continual runoff in that case. And in the soil column itself, it was a lot slower. So this one especially is where you saw some curvature in those lines. And then overall, by increasing the hydraulic conductivity, just looking at these sort of plots, they're fairly similar to the default simulation. So with this change, we think that this was a fairly insensitive choice to make, but obviously there are discussions about that as well. So if you continue to the next slide, just to wrap up kind of what we've been talking about, we found that the capillary retention parameter actually had pretty large effect on both when runoff occurred and also how the snowpack wetting behaved more erratically in a cyclical fashion with the diurnal cycle. The saturated hydraulic conductivity overall seemed to be the least sensitive. We saw from the time series of the drainage in the snowpack, these were the most similar. And then also looking at the liquid water content of both the pack and the soil, they appeared to be, just by the eyeball test, pretty similar as well. The differences between these simulations also varied most dramatically at the beginning and the middle of the melt season. As we look at these, that seemed to make a lot of sense to us. And overall, looking at the fractional liquid water content was more effective at visually tracking the movement of water. You can do temperature, but obviously there are very small changes in the temperature throughout the middle of the snow season between the snowpack and the top layers of the soil. You can also do liquid water fluxes, but those vary dramatically from very small to very large. So that scale makes it really difficult to look at what's happening in your snowpack. And then finally, these changes in the capillary retention, saturated hydraulic conductivity, and meltwater exponent, they're subjective. To make this a more fair comparison and say which parameter is more sensitive than the other parameters, you have to really have some basis on the decisions that you make about tweaking these parameters. So, for example, a doubling in the hydraulic conductivity didn't seem to make much of a difference, but also that may have been a more minor change in a parameter than is usually seen when you actually parameterize that. So that's something to keep in mind as you continue to twist the knobs on your model. And with that, I think we're done. So we'll take any questions.
Thank you. Any questions while I find our second to last presentation? All right. Can Devin, Scout, and Tim all be heard?
Yes, hello, can everyone hear me?
I can see Tim. I can hear Devin. All right, excellent. I'm gonna
Do we have Scout?
It says she's talking, but I can't hear. Can anyone else hear her?
Can you hear me?
Yes.
Yeah, I can hear you.
Great. So I'm Devin Eckberg. This is Tim Yoder and Scout Heck. And we're going to look at vegetation variation and canopy conundrum. So on the next slide, the homework we've done showed that the parameterization can have a huge impact on the model, and homework 2 showed that the clearings and forests respond differently to the same parameterization. And the parameterizations modeled in the homework still show pretty different values than the observed SWE. So we decided to try look more into what might get the model to better fit observed SWE with the canopy and open. And we focused on parameters that had to do with vegetation. So we ran the model with all of the canopy structure parameterizations as well as all but one of the shortwave radiation through the canopy parameterizations. And on the next slide, so that for vegetation roughness, length, and displacement height, there was two choices. It was the Robach BLM 1994 and CMQJRMS, and then canopy shortwave. We ran NOAA MP, CLM 2-stream, ML scatter, and Beers law. Then for the next slide, the parameterization for vegetation roughness, length, and displacement was various empirical functions of exposed vegetation area and canopy height. On the next slide, it goes into a little bit of the Chartery and Monteith. The CM model modeled exposed vegetation area and canopy height as a function of aerodynamic resistance and buoyancy. And on the next slide is a little bit more of the derivation, but we'll just move on to Robach. The Robach model models displacement height and roughness length related to frontal area index, or FAI. And this paper that we were looking at used observation data to fit the estimation and generate the coefficients below. And then the next slide is just a little bit more of the derivation. And then Tim will discuss a little bit of the results from manipulating these vegetation traits.
Yeah, so if you go to the next slide, yeah. So our results are actually going to model pretty similar to the third groups. So if you see in this derivation, one is a log based equation, the other one is an exponential based equation. So you'll see that some of our results are similar to what they found, and some are a little bit different. So the first plot is just the snow water equivalent. In the clearing site, we were using the UMQuad data set where we had the observational data from the SWE available as well. So you can see that both parameters perform almost identical to each other with a slight difference in the end of April. But that's kind of to be expected since there's not much vegetation in the clearing. So if you go to the next slide, we looked at the difference in the forest model. You can see both models perform pretty similarly, and they follow the observation data set pretty well up until about January. Then they all diverge pretty rapidly. So both of our models continue accumulating snow past the observed set, where the observational set starts declining. And then the Robach model stays really high in accumulation, whereas the CM model tails off a little bit. So since we also did not have the first group's suite graphing tools, we had to do all the manual graphing ourselves. So if you go to the next slide, we're just zooming into that area where you see the big divergence. It's just one particular event, it seems, over the course of a few days that really caused the difference in the two models. You can see the leading up to that point, they follow pretty closely with slight variations, and then they diverge pretty rapidly. So like the third group, we wanted to investigate that point. And if you go to the next slide, you'll see what we thought to be one of the biggest differences, which happens to be the exact same graph apparently as the third group with slight differences. So as Dr. Link was saying, this could be a rain on snow event where you see a large increase in positive snow sublimation in the CM model, which I believe was the logarithmic model. But contrary to the third group, if you go to the next slide, we see only a slight difference in the latent heat transfer between the two models. And on the date of concern, which is about the 1st of January, you see a positive latent heat transfer in the CM model, whereas the R is on the negative side, which I believe is similar to what the third group found. If you go to the next slide, this is the sensible heat transfer, which looks really different from what group 3 had. So in this particular, in these two simulations, the sensible heat transfer tracked each other pretty closely. You can see in that first bit of January, there's a slight difference in the sensible heat transfer, but it appears that the sublimation was the main difference between the models. And if you go to the next slide, I believe we have, just drainage we looked at. You see where that water ends up going in the R model, there is a lot less. So there's more water staying in snowpack. If you go to the next slide, just right on, yeah. We can see that the surface temperature for both simulations stayed pretty consistent throughout the whole year. This is looking at the whole year instead of just those few days. But you don't see a big spike into the positive like you did, like you saw for the difference in the logarithmic and exponential parameters. They stay fairly consistent, so it must be something that's happening at the bottom of the snowpack, is what we surmised. I think if you go to the next slide, Devin's going to continue talking about our parameterization runs.
So moving into the choice of canopy shortwave radiation method, there's a couple more options. There's the NOAA MP, which is the full implementation, including albedo, CLM 2-stream, UEB 2-stream, the NL scatter, and Beer's law. And all of these are actual applications of the Beer's law. They're just a little bit different. On the next slide, Beer's law is just the simplest application for the shortwave radiation through the canopy, and it's the base for which the other models are built off of. Figure on the right shows the processes as it's modeled by Vic. NOAA MP on the next slide. There's a full implementation which factors in albedo, and that figure on this slide shows the flow chart of the radiation subroutine. So you see albedo factored in there, and it calculates everything out. And then CLM 2-stream on the next slide is the community land model, and it's a function of the diffuse fluxes and direct beam and diffuse grand albedos. It also has like the exposed leaf area index and stem area index, and optimal depth of direct beam per unit leaf and stem area. The next slide has the NL scatter model, which was developed to account for scattering and multiple reflections. And Scout will discuss the implications of these parameterizations.
Thanks, Devin. So on the next slide, there we go. For the shortwave parameterization in the forest, Beer's law gives a consistently higher SWE than the other choices. It's kind of small, but it's up in the top left graph. NOAA gives the next highest, and then the NL scatter and the CLM has the lowest SWE. In the clearing, NOAA has the highest SWE, while the others are pretty much identical. And so you can see, compared with our homework where we did the long wave, the SWE is a lot more sensitive to the choice of long wave than the choice of short wave. And next slide. Thanks. So one possibility for why the SWE was so great in the Beer's law scheme is the drainage. As the forest plot shows at the bottom there, the CLM and NL schemes have the highest drainage, and Beer's has the lowest. So if you click one more time, it'll zoom in. So there it shows the CLM and the NL have the highest drainage, and Beer's law has the lowest, which could account for the greater SWE. But it's also there's also a higher drainage of NOAA in the clearing one, which is odd because NOAA had the highest SWE too. So that's kind of confusing. So then the next slide. So this one shows that the surface temperatures didn't vary very much, and neither did the sublimation in the clearing in the next slide, except for in the forest, the sublimation alternated between which scheme was the most extreme at each spike. So you can kind of see the different colors on the spikes at the bottom. And Beer's law had the lowest magnitude overall of the snow sublimation. And that's all we have.
Thank you. Are there any questions? All right. Then I'm gonna pull up Jonathan's. I have two versions, but I think they're the same. Jonathan? There you are. I see you. I see you. I can't hear you. I still can't hear you. No. Try something.
I think he muted himself.
I can't hear you. You gonna chat? You want me to read what you're gonna type? Or you want me just to try to give you a presentation for you with based on the slides? You can call in. You can call my number. You can telephone. You had an idea. Okay. This is the greatest challenge to this class. Can you pass the technology? So while Jonathan, hello?
Can you hear me now?
We can hear you. Excellent.
Okay, there's no video on this computer, but
That's okay.
But you can hear me at least. You saw me for half. I have a computer that I can get video and a computer I can get audio, but not a computer that can do both.
Excellent.
Yes, well, I guess I am bringing up the end here. I appreciate the calls that everyone apparently wanted me in their group, but I didn't have time to really contribute much, so I didn't want to sort of jump in on the last minute. So thank you for that. I was just going to do, I just basically did some quick look about how air temperature adjustments affected sort of the snow water equivalents in some of the models that we have generated. And so go ahead, next slide. Yep. And so functionally all I did was adjust air temperature values, but I wanted to sort of have some basis for what I was adjusting to. So I looked up the third Oregon Climate Assessment Report, and they have in their they've modeled the impacts of the a few different of the climate change simulations on average temperature change. They did the RCP, the representative concentration pathways of, there's like multiple RCP values, but with the 4.5, they had the mean annual temperature is projected to increase on an average 3.6 degrees Fahrenheit, and by 2050, and I'm sorry, and the 4.6 degrees Fahrenheit by 2080, and with the RCP 8.5, which is a more severe projection, it was 5 degrees Fahrenheit by 2050 and 8.2 degrees Fahrenheit by the 2080s. Next slide. And so the first thing is, like, those are obviously Fahrenheit degrees. I mean, who uses Fahrenheit anyway? And it's also not necessarily fair to say that this is a overall temperature change, because summers warm more than winters, and a simple addition to like a baseline temperature, air temperature value isn't really representative of how all this works, but that's what I did anyway. And so with the adjustment to Celsius or Kelvin degrees, the RCP 4.5 2050 adjustment is adding 2.02 degrees, the 2080 2.58 degrees, the RCP 8.5 is adding 2.8 degrees, and the RCP 8.5 2080 is 4.59 degrees. And you can see this chart here is one that everyone should recognize, because this is just the observed and simulated snow water equivalents in the clearing and forest of the Umpqua site in Oregon. So this is just the data that I added to, and so I just adjusted the air temperature values in that model, and even getting this far, I was very proud of myself. And, and so this is, you can go ahead, next slide. And like throwing that back in, this is for the clearing sites, with the dotted black lines being the observed and the blue line being the simulated. So that's the same that was in the original chart. And the rest are the impacts of the snow water equivalent with the temperature addition. And even with just a 1 degree Celsius increase, the snow water, which is that green line, it just dramatically reduces the amount of the snow water equivalents to the point where even with the RCP 8.5 and 2080 projections, basically almost eliminating all snow. So when I was thinking about this, I was like, well, I'll just crank up the values until the elimination of snow is projected, but that's basically already in the projections with the RCP 8.5. Next slide. And I just did some average values. I wanted just to sort of see the average trajectories over each month of these, and just to sort of give it a more smooth, and we'll come back to this chart in just a little later on in the presentation. Next slide. And this is the same thing with the forest. Obviously, what we had with the observed and simulated values in the first place were quite a bit off with the black dotted line and the blue line. But it's almost the identical same pattern of even with a 1 degree increase with the air temperature, the snow water just drops dramatically, and it's a smaller difference as the increases change, as the temperature increases with the decrease in the snow water equivalents. Next slide. The average values for the forest, and we're going to come back to this. Next slide. And so this was something that was, this was the average values of the snow water equivalent in the forest and the clearing at each site, and all of the forest values being the solid lines and all of the clearing sites being the dashed lines. And you can see one thing I was to note is that they typically all switch as to in about February where the clearing had more snow and the forest sort of holds onto the snow a bit more after February. So next slide. And like comparing it back to our original data that we had, or the original simulation graph that we had, there is, you can see that the clearing in our original data had a higher snow water equivalent value all the way up until like about March, and then the forest was like holding on to more snow. But go ahead and do next slide. But as we're increasing the temperature, we are like setting back when the forest, which sort of makes intuitive sense. As the temperature increases, the forest becomes more of the reservoir for holding on to snow later in the season, whereas in the clearing sort of melts off more rapidly in the simulations. And that's all I have for you.
Thank you. Any questions? I have a question.
Yes.
Jonathan, did you change the long wave as well as a function of the temperature, or was this just a test of changing the temperature?
This is just a test of the temperature, and I wouldn't submit this to any sort of publication because there's about 1 million different issues with it, but I kind of just wanted to just look at the pure effect of temperature.
No, it's impressive how sensitive it is. It's simply temperature.
Can I ask a question real quick?
Sure. Maybe
I have. So yeah, well, you were talking about the fact that the forest tended to hold on to snow a little bit, and it made me think about how you know, the sticky snow or whatever, the interception. Did you see a clear mark between when your snow was falling as rain instead of snow, and then also the separation between that and instead the temperature driving melt? Did you see like a clear separation between one RCP and another, like one snow is actually happening but it was just melting more, and one snow wasn't actually happening because it was falling as rain instead?
No, I didn't get much into an analysis other than that sort of very superficial temperature. And there's certainly a lot more avenues that can go into this.
Thanks.
Any more questions? All right, so we are almost out of time. I want to say first, thank you to all of you. Those were great presentations. I'm really impressed. I want to remind you to go onto Canvas and give each other feedback on the presentations before you forget them. So make sure you do this sometime before midday tomorrow, please. We do not have enough time for me to tell you the entire secret to what was happening with the 2-layer thick model, but my slides are posted. You can go through them if you're curious and see it is the special case of snow without a layer. You can see there was actually no snow layer. And so I walk through in the slides. I think you can figure out what it is. I don't quite have enough time because I want to just make sure I cover logistics before I turn you all loose. Also make sure in the assignments that you also fill out the final survey. So you've got feedback for each other, and then this one that's reflection is just, I'm planning to do this again next year. You guys were the beta test class. So any thoughts you can give me on how to make it better would be great. And then if I've got 2 minutes, I posted a movie online, but it's only 1 minute long, and I'm really proud of myself because I've been thinking I should make my lectures into movies all along. And so I will show this, and if you can't stay, no offense. If you can, this is my very exciting movie, which is supposed to be a conversation starter to figure things out, and we'll see if it works. Any other questions? I'm still working through all the grades. Feel free to contact me if there's any logistics issues beyond this point. This is our last day together. Anything else before I show you my exciting movie that I made with my phone? Yeah. Okay, here's my exciting movie. All right, I am going to tell you the story of my car on my street. And now we live in Seattle, and so usually in the winter it's pretty cloudy, but sometimes it's really clear. And our car is parked on the street, parked by the sidewalk here, and we have this big fir tree. So, evergreen. Okay, so now comes a clear night in Seattle, and it turns out that we get ice all over this side of the car and no ice at all on the windshield on this side of the car. So what is happening? Right, anyone know the answer? Yeah, so it's related to your homework too, and the tree is emitting long wave radiation. And so the reason you found on your homework too that your long wave radiation from the sky mattered less under the canopy is something called the sky view factor, which you can see. Here's a picture in my PowerPoint. It's when you look straight up, how much of the sky do you actually see? This is what my car is experiencing, that this side is actually seeing the sky. It's losing long wave radiation. There's no clouds, it's clear, so there's no long wave from the sky. The tree is emitting long wave radiation and is keeping this side of the car warm enough it doesn't get any ice from the cooling. If we change the parameterizations from long wave from the sky, it's gonna affect this side of my car. It's not gonna affect this side over here, because this is the tree which emits more closely to air temperature near the ground and is less affected by the sky. And there's a few more slides if you're interested in my slide deck here that talks about shortwave versus long wave radiation. And in the interest of time, I will let you go. Feel free to contact me with any questions that come up after this class, and thank you all for bearing with me.
Thanks, Jessica.
You're welcome. Have a good rest of the quarter. And if people are going to be at AGU, maybe we can all say hi in person. Send me a note if you're going to be at AGU, and I'll try to set up a class in-person meeting. We can all say hi. Bye-bye.